Hello everyone, this is Dharmendra Reddy MS from Department of CSE from Sri Venkateswara College of Engineering. Today let's see Introduction to Undecidable Problems. In the realm of computational theory, the fabric of logic and problem-solving waves are a complex tapestry, and within this intellectually lies the concept of undecidable problems. They are problems for which no algorithm can be constructed that always leads to a correct yes or no answer. The study of such problems is not merely an aesthetic pursuit, it is fundamentally understanding the limitations of computation and decision making in machines. The journey in the world of undecidable problems begins by acknowledging that some questions are beyond the reach of decisiveness framed by Gödel's incompleteness theorems and brought into the spotlight by Alan Turing as we navigate through the intricacies of these problems. We unravel the rich layers of complexity that both challenges and advance the field of computer science. Definition of RE Recursively enumerable problems. Algorithm existence. Recursively enumerable problems are characterized by the existence of an algorithm that can enumerate their solutions all through it cannot necessarily decide if a particular solution is not in the set within a finite time frame. Recognition over decision. RE problems focuses on the ability to recognize correct solution as opposed to definitively deciding all potential instances of the problem efficiently, separating them from decidable problems. The halting problem. The potential examples of an RE problem is the halting problem, which confirms the existence of a program's termination but cannot determine non-termination universally. Examples of undecidable problems. Halting problem. Alan Turner's halting problem stands as a monument to undecidability, determining whether an arbitrary computer program will ever halt or continue indefinitely is undecidable by any computation. Antecedents problem. Originated by David Hilbert, the antecedents problem seeks an algorithm to determine the truth of first-order logic statements, a notation proven undecidable by Turing and Alonzo Church. World problem from groups. The world problem asks whether two expressions can be proven equivalently within a group structure, a problem shown to be undecidable from general cases. Explanation of the problem being discussed. Problem introduction. The problem at hand is a sequence of logical operations with an undefined endpoint, an algorithm that cannot ascertain its general conclusion, exemplified by the inscrutability of program termination. Dissection. We then dissect the problem into its computational consequences, analyzing inputs, process, and the elusive nature of its output, proven by the rigidity of algorithmic formulation. Theoretical implications. The theory implications vast aspects of logic where proof and function classic confronting the practical finite against the theoretical infinite. Overview of the problem's properties. Computability. The problem possesses a malleable boundary of computability with some instances faltering under algorithmic weight, thereby rehighlighting its hairy nature. Non-determinism. One must grapple with the inherent non-determinism, a property that showcases the problem's alignment with indeterminacy and unpredictability within computational systems. Inherent ambiguity. It's imbued with ambiguity in its formulation, necessity a deeper understanding of problem parameters and computational limits. Turing completeness. This reflects the shades of Turing completeness where the problem's complexities are vast enough to encap the computation of any computable problem. Proof that the problem is RE. Enumerative process. The existence of an enumerative process that lists valid instances is the cornerstone of proving the problem status as RE. Verification mechanism. An effective verification mechanism demonstrates the problem solutions can be recognized a hallmark of RE problems. Turing mission construction. The hypothetical construction of an non-terminating Turing mission offers a proof concept cementing the problem's canonical RE status. Implication of the problem's undecidability. Limitations on algorithms. The recognition of the problem's undecidability craves out boundaries for algorithm pause, prescribing a humbling checkpoint on computational ambition. Theoretical constraints. This foretells a fundamental theoretical constraint prompting a reevaluation of expectations within computer science and the scope of artificial intelligence. Study of complexity. It catalyzes the study of complexity classes, pushing the exploration of P versus NP problems and other landmarks in computational theory. Applications of the problem in computer science. Programming languages. The problem's exploration inspires programming language development, especially those that embedded logic constructs to avoid undecidable computations. Robotics and AI. In robotics and AI, the problem guides design principles emphasizing heuristic approaches over the deterministic algorithms to navigate complexity. Cybersecurity. Cybersecurity utilizes the conundrum of undecidability in developing encryption methods leveraging computational hardness protect information. Challenges and limitations of solving the problem. Non-terminating algorithms encounter infinity loops without resolution, confounding solution efforts. Practical computability. The dilemma between theoretical possibility and practical computability comes to the fore, often resulting in unsolvable real-world implications. Limited heuristics. Heuristics provide approximations, yet they also present limitations that undermine assurance in outcomes. Resource constraints. Constrained computational resources compound the difficulty in addressing inherential undecidable problems. And let's see conclusion and future directions. The odyssey through the landscape of undirectable problems that are recursively enumerable has divulged that these enigmas, as much as they baffle and bewilder, also impel the field forward. They elicit deeper questions such as the nature of computation itself and awaken curiosity about what lies beyond the decidable horizon. Future directions beacon, which promise and challenge alike as our digital universe burgeons in complexity, so too will our approaches to these riddles, whether through quantum computing, emergent forms of AI, or unforeseen modes of problem solving. The quest to understand and maneuver through these problems remains a cornerstone of computer science ongoing narrative.